Thank you for the introduction, and hello, everyone. As said, I'm Syed Zia, security engineer and cryptographer at enoka. Today, I'll be presenting you a novel concept for securing device-to-device communication. We call it device private networks. So the highlight of my talk would be how we can use zero trust in developing such solutions. I think the font is not embedded in the slides, but for now, I think we'll ignore that one there. So who are we? enoka is a cybersecurity startup, basically NCSA alumni startup, and we provide cybersecurity solutions for securing machine-to-machine communications. The unique technology that enoka produces has been supervised by NCSE, and we partner with the market leaders in the domain. The question arises, why are we here today? Just like everyone else, we're also trying to put our share and contribute in setting up the foundation to set the gold standards for IoT security. enoka is already providing solutions in a versatile domain. So IoT is a heterogeneous world, and the solutions we provide range from secure command and control that we call Ranger. We have secure remote control, ROC. We have secure IoT telematics, health, usage, and monitoring. And of course, on infrastructure level, we're talking about secure intelligent transport systems. Well, let me take you back to perimeter-based security. It might ring bells because everybody has grew up around with the perimeter-based approach. The idea of walled garden worked well when we had a confined perimeter and we had firewalls and intrusion detection systems or prevention systems to just make sure that nothing leaves the network, nothing enters the network. And this security assumption was fine for that time. Still in use, but what we're talking about now is bigger. It's actually way bigger. So we've been talking about Internet of Things, but it's actually Internet of everything. So everything is connected, and it's not only things. We have people, we have processes, we have data, we have network. So second problem is your data is not in one place. So now you cannot confine it into a box. You cannot confine it into a boundary. Sensors are remote. You have edge computing platform somewhere else, and then you have cloud computing done somewhere else, and then you have to send back the actuations. So your data is always on the move. Modern working practices like work from home, bring your own device, remote location. Even for today, I was working with my work laptop in a coffee shop. Before that, I was staying at a hotel overnight. You never know. You can't put me, my IT administrator in Belfast office, he can't actually put me into his firewall or jurisdiction. Data exchange in bulk. So now we're not talking about a little bit of data, it's on infrastructure level. So we're talking about smart cities, smart homes, smart wearable. So moreover, it's always on the move. So autonomous cars, smartphones, smart drones. Now your devices are basically not in a confined boundary as said, so your perimeter-based approach doesn't work very well there. So we need a new way of thinking on that one, and we already have a new security paradigm that is called zero trust. So for zero trust, the security assumptions are it doesn't have any traditional network edge. So that fully sits on the problem we were just looking at the previous slide. Your network could be local, it could be cloud-based, it could be hybrid, or it could be remote. Moreover, the network user is treated equally as if it was on the network or outside the network. So for that, the user is authenticated, authorized, and has to comply with all the access policies for every request. Now, to achieve zero trust, there are a few principles that you have to fulfill. And there are three main principles for that. Number one is continuous verification. And you always authenticate and authorize a request. And not only do that, you have to limit the blast radius. So I think a lot of platforms like GitLab and stuff, they already do just-in-time access. So you have token-based access. You limit the user for a specific resource and specific time. And the third one is you always assume breach. So your network is always under breach. And for that one, you have micro-segmentation of your network. And that's where the concepts of self-healing networks and they arise. And we've been hearing a lot of AI stuff today, and we know it's not mature, but for zero trust, we do encourage behavioral data collection, and not only on the devices, but your whole entire IT stack, ranging from identity to the networks. So NIST, National Institute of Standards Technology, has already published a standard which is vendor neutral, which means it's not linked with any vendor. Anybody can deploy it. It's reviewed by security experts. It's comprehensive enough that anyone can understand that. And it's user agnostic, which means it's not targeted for government organizations, but it's for any small enterprise or any business. So the figure you see on the right, I have shamelessly stolen from the NIST document. And it actually highlights the logical components in the zero trust architecture. So we have seen the concepts, we have seen the principles. Now we are going to look how to actually deploy it, right? So ignore the things that are coming on the side. We'll explain in the next slide. But take a look at the policy decision point. So that's where your policy engine and your policy administrator sits. And they enforce access policy for the system or the subject that's trying to access the enterprise resource, right? Keep this figure in mind. I've tried to simplify it for you. I don't know if I've complicated it. But the idea is to fuel zero trust with AI. And as said in the morning talks, we don't have any mature solution for AI, right? But there are possibilities that we can use to actually fuel and accelerate the zero trust architecture. So for instance, you have activity logs, and instead of flooding your system with redundant data, you're actually performing anomaly detection, and we have solid tools for that. Risk-based authentication can be used for identity management. So instead of just doing authentication on login and password, you have other factors like location, IP address, and risk-based, that one. Threat intel can be improved with attribute-based authorization. So it's not just if you're on the network, just give them the access. You have different attributes that you can set your access policy on that. So similar, like you can use AI to provide recommendations on compliance and regulations, recommendations on the certificates that are in phishing emails. They can be flagged, and you don't even have to verify the certificate. You already have a repository that, right, they're benign, they're not valid certificates. And then for continuous diagnostics, you already have next generation extended detection and response tools and secure event and information management system tools. So the idea to show you is that think of an AI plane in the middle. So you have a machine learning algorithm. So the filter rate is actually going to your system, to your architecture. So you're not flooding it with redundant data. That is not useful. So what you're doing is you're using AI to make it smart. Now, one thing I think we all are talking about is device level. So we'll go into that one, but look at the challenges first. Zero trust is yet a philosophical concept. So we don't have a one ready-made off-the-shelf solution that I could say, oh, let's use it for IoT. So there's not tailored solution for IoT yet. But there are few solutions that are claiming to be zero trust network access, and they're doing good job, but they're basically broker-based solutions. So they use cloud or third-party applications that pipe your data through and allow you similar features of VPN, but more advanced. So it's a zero trust network access, but it's not a fully zero trust architecture that we saw in the previous slide. And using those third-party clouds and those broker services, you're moving towards potential points of failure. User credentials. So again, going to device level, user credentials are user-centric. And what if the device itself is lost and somebody just tweaked the firmware and you have got, something else running on the device, but your user credentials are still valid? And in broker-based services, there's a concept of zero trust admin. Now there's an admin who is an attractive target. So you got the zero trust admin, and that's it. You lost the whole essence of zero trust architecture. Let's talk about device private networks. The security blueprint for DPNs, or device private networks, is based on zero trust architecture. So those three principles are exactly the same that we saw in the first slides. So we verify explicitly, authenticate and authorize every request. We use least privilege access, just in time, just enough access, and assume breach micro-segmentation. The diagram you see on the right, again, apologies for the formatting. It's due to the embedded font problem. So what I'm trying to show here is the areas of defense in zero trust architecture. They range from identity, applications, network, infrastructure, and so on. But one thing you might see is they are still not linked to the device. And what we're facing the problem in IoT world is device level gap. With DPN security blueprint, what we're trying to emphasize here is that the identities should not be given. They should be generated. So when we talk about user credentials, we're talking about login IDs and passwords. If we talk about VPNs, we have IP addresses as your identity. But what we're trying to say here is, Dr. Masebi mentioned about POFs and stuff, so there should be a hardware root of trust. And again, when we talk about attribute-based or risk-based authentication, you don't have like one factor. You can have multiple ingredients that you can extract from a device and kind of generate the identity from the device. So you don't rely on given identities, you generate them, and they're dynamic for every session. Since for IoT, you're going to have a lot of sessions when we talk about micro-segmentation. We'll see that in the next slide. So step one for DPNs, you generate immutable digital identities. So they can't be tampered with. You can't just take the device away and put a firmware on it. It's actually being generated from the device itself. Based on that, you perform mutual authentication. You micro-segment your infrastructure, kind of configure the trust level and the trust boundaries. So you have different sessions, different micro-segments done. So there's not one intruder coming in and kind of colluding the whole network. So you have the concept of micro-segmentation there. And then from there, you have unique DPN identities and unique session keys for each of that micro-segmented network. And of course, based on zero trust principle, you're authenticating and encrypting all the messages and data sent over the network. Coming back to the same diagram, quite simplified one. What, again, I'll emphasize here is a subject. So subject is a human. I know we're talking about human and AI partnership and everything, but my talk, the idea is to make device smart. The device itself self-sufficient, that we do not require a human to be supervising it all the time. So let's remove the subject from the loop. Oh, there's some fancy transitions, so stay with me. So how about if I push down the policy engine or the policy rulebook, machine learning-based playbook, whatever you want to call it, onto the device itself. And now all the hard work is being done on the cloud or wherever you want, where you have resources, and then you update the policy book or the rule book periodically whenever it's needed. Well, that's a lot of theory there. Has anybody been to Belfast yet? Right. So you might recognize this map. It's the Queen's Road. That's the Titanic quarters. We have the Brightest Light. We have HMS Caroline. We have Titanic distilleries, and above all, we have enoka right there. So the idea is it's a quite active tourist attraction, and we have a project, Harlander, that enoka is providing cybersecurity. So the idea is there would be an autonomous shuttle that will be taking passengers back and forth from Titanic train station to the docks, and it's going to be not only data-based. Now you're talking about lives. Now you have people who are there to have some good time, right? And when we say, oh, we're providing cybersecurity, it's just not like you just give somebody like that. No, it's actually collaboration of different roles, and a lot of different organizations contribute to that. For instance, infrastructure in this case is provided by Belfast Harbour. It's a 10 million funding worth project. OGSA, they're providing the autonomous driving system. I think in the morning talks they were talking about that still machine learning is not smart, but there are companies that are providing solutions. So they have an autonomous driving system that will allow that shuttle bus to go on the track and drop and pick up the passengers. We have Eversum who are actually manufacturing that shuttle bus for us and also kind of incorporating the OGSA technology into the shuttle bus. And British Telecom, they're having a vehicle security system, and they're also putting down a virtual SOC, which I'll talk about later. What is enoka doing there? They're providing secure telematics, secure health and usage monitoring systems, and secure automation and response. Now, bear with me. Now there's where we're going to actually visualize the DPN. I know it's a lot of information on one slide, but the idea is to show you how that works. The main thing that we're ignoring is the device level again. Inside vehicle, you have controller area network, you have a CAN bus, and that's the most vulnerable part. So the first DPN, the device private network, is going to sit on the vehicle and secure in-vehicle communications. The second DPN is between the autonomous shuttle and the Eversum doing the security, health, and user management system. And that is part of the first DPN as well. So there's micro-segmentation, but you can see how the slicing is done here. Then DPN 3 is between OXA and autonomous shuttle, and then DPN 4 is between BT and there. So you see the communication between all these networks is independent. It cannot be interfered. And now coming back to the virtual SOC concept, the policy book that I pushed down. So we have Vehicle Security Operations Center that is operated by British Telecom. And the vehicle itself is already having a rule book that it's driving on the road. It knows what to mitigate, all the attacks. But now there's something new that's come up. And your machine learning or AI-based, or the slide we saw in the start, how we can fuel with AI. So the latest or the updated policy book can always be pushed down to the vehicle, making it smart. So the concept that we're trying to make here is that make the devices smart, because we're talking about a smart world. So we need to make our devices smarter. Based on that, I'm going to move to a bit of a controversial topic. So let's compare DPN, or device private network, with state of the art. Because we do experience a lot of people, they're still very happy with the TLS, transport layer security. And they're like, oh, what's different in DPN? TLS is doing the same thing. Secure connection, I see a padlock on the top, I'm safe. So let's take a look and compare them on communication capabilities and security capabilities. Stay with me. If you feel the results are biased, you can catch me on the coffee or we can have a chat about it. So security protocols, transport layer security, virtual private networks, again, widely used, and DPNs. So what I'm going to do is I'm going to highlight the highest or the superior most security requirement. So TLS is server client-based approach, yes. VPN server, we have a VPN server, and we have DPN that we are proposing it to be decentralized. Supported communication type, it's mostly unicast, one-to-one. VPNs do support multicast, and DPNs are configured for broadcast communications. As I gave the example for CAN area network, so that's a broadcast medium. Or in drone scenario, you're actually doing the broadcast communications. So integration with other protocols, they're pretty much all very nicely integratable. So they're all on the highest requirement there. Network micro-segmentation, TLS doesn't provide any segmentation. VPNs do, some of the advanced ones, and DPNs also provide micro-segmentation. Access policy engine, TLS doesn't have any access policy engine. VPNs have a fixed policy engine. Right, I'm running out of time, so I'm going to be a bit quick on this one. And DPNs have dynamic or adaptive policy. From the security perspective, which is more interesting to me, since that's my area, and also I think Dr. Musabi's area as well. So TLS asymmetric key, unless we come up with some post-quantum primitives and we count them secure. But yet, they both are based on asymmetric, TLS and VPN. There are a few papers on moving to post-quantum, but I'm talking about the latest standard, TLS 1.3 or OpenVPN WireGuard. DPNs use symmetric key for authentication, so you don't have the problems just like asymmetric key. They all provide data security levels as authenticated encryption, which is pretty good. When we come to maximum security strength, it is basically for asymmetric algorithms, it goes down to 112 bits, and it's not by me, it's by NIST. We have a publication 800-57. I'm also happy to talk about after the talk. So DPNs provide 256-bit maximum security strength. Authentication, traditional one-time. In DPNs, again, going back to zero trust security, we continuously verify, we continuously authenticate. Authorization, TLS doesn't authorize, you're authenticated, that's it, you have a secure connection. For VPN, once you're on the network, you have access to all the resources. But for DPN, you have granular access control. So as we saw in the Harlander, you had different DPNs for each communication channel and access to different resources. Quantum resilience, again, until we get a post-quantum solution for them, they're yet susceptible to quantum attacks. However, DPNs use symmetric key cryptography, and they're not quantum vulnerable. Identity masking, I'm going to give a yes to VPNs here, which is, again, you're masking your IP address. But what we're talking about here is actually generating an ID from your device ID, which is bound to your device. So I think I'm going to leave on that controversial note there, and I'm keen to look what thoughts you have about it, any questions, any feedback. And also, I'd like to credit my team for all the hard work. Thank you very much.